Sometimes, to count efficiently, we need to use division or subtraction. This video shows how. As our first example, let's figure out how many ways there are to seat 6 people at a circular table. So if we call the people A, B, C, D, E, and F, this would be one way of doing it. And this would be another way. But this way would actually be the same as the way right above it, because everybody has the same left neighbor and right neighbor. It's just that the table has been rotated by 2 spots. So to figure out how to count this, notice that there's 6 choices for who sits at the head of the table. No matter who sits at the head of the table, there's going to be 5 people who could then sit on their, I guess it would be on their left, on the side of them over here, right? Because they're not 6 choices anymore because you can't sit next to yourself. Okay. Now, once I've chosen who's going to sit here and who's going to sit here, there's 4 choices left for who sits in the next spot, because I've already used up 2 of those choices. 3 choices for who sits here, 2 choices for who sits here, and once I've chosen all those people, there's just 1 choice left for who sits in this spot. So the total number of ways of sitting the people around the table is going to be 6 times 5 times 4 times 3 times 2 times 1, which is also called 6 factorial. But wait a sec. If we count all these ways, then we're counting this green seating pattern and this purplish seating pattern as distinct, right? And we need to count them as the same. In fact, we've counted the seating pattern 6 times over. 1 time for C being in this position, 1 time for C being in this next position, 1 time for C being here, and for C being each of these other spots, right? In other words, there are 6 ways to arrange the people in this order around the table where they have the same left neighbor and the same right neighbor, but C is just in one of any of these 6 spots. And every other seating pattern is counted 6 times when we count it like this. For example, this seating pattern is counted once for A being at the top, once for A being in this spot, and so on, just with the table sort of rotated all those 6 ways. Every single seating pattern we've counted 6 times instead of 1 time. So how can we fix that? We just divide by 6. So the actual number of ways is going to be this number divided by 6, which is the same thing as 5 times 4 times 3 times 2 times 1, or 5 factorial, which works out to 120. We use division to get rid of the overcount because we counted each way 6 times over. Our next example, we have a class that contains 16 math majors, 12 comp sci majors, no other students, and 5 of the students are double majoring in both math and comp sci. So how many students are in the class? We can use subtraction to find out. Think about this Venn diagram, where here are the 16 math majors, here are the 12 comp sci majors, and we have 5 students majoring both. The total number of students is then 16 plus 12, except we're counting those 5 students twice, so we have to subtract them off. That gives us 23 students. This principle of subtraction is also known as the inclusion-exclusion principle. Why did we subtract here and not divide? Well, only some of the people were being counted duplicate times. It wasn't that everybody was counted twice. If everybody had been counted twice, then we would have been able to divide by 2. So as general principles, when each item is counted with the same number of duplicates, we can divide by the overcount. In the table problem, all the arrangements were counted 6 times, so we divided by 6. When only a few items are counted twice, then we can subtract the number of duplicates. So in the comp sci math major problem, we subtracted 5. One common application of the division problem has to do with anagrams, or ways of arranging the letters in a word. If we want to ask how many ways there are to arrange the letters in the word Hogwarts, not worrying if that arrangement actually makes a real word or not, then we can just count up the number of letters, 1, 2, 3, 4, 5, 6, 7, 8, and then argue this way. There are 8 letters that we could put in the first spot. For each letter that we might put in the first spot, there are 7 possible letters to put in the second spot because we already used one of the letters up. Each way we have of picking a first letter and second letter, we have 6 choices left for the third letter, then 5 choices left for the next letter, and so on. So the total number of ways of arranging these letters is going to be 8 factorial. We might think that we could use similar reasoning on the word Voldemort. Voldemort has 9 letters, so if we use the same reasoning, we'd say that there were 9 factorial ways of arranging them. But this word's a little bit different. Notice that in Hogwarts, each letter was different. But in Voldemort, the letter O occurs 2 times. So in this 9 factorial ways of arranging 9 objects, it's like we're saying that this arrangement is different from this arrangement. They don't look any different, but I might say, well, we counted them as different because in this first one, we did the first O here and the second O there. And in the second arrangement, we did the second O there and the first O there. If we're really counting it as 9 factorial, then to have a full 9 choices for the first letter, we'd have to be considering those 2 O's to be distinct. But in fact, the 2 O's are identical, right? We can't tell which between these 2 ways, and we couldn't tell between these 2 ways, or any other 2 ways where the only thing that's changed is that the O's are in the other order. In other words, when we do 9 factorial, we've counted each arrangement twice. To get rid of the overcount, we're going to need to divide. So the correct answer is 9 factorial over 2. What about arranging the letters in the word Aranya? There's 6 letters. If we were just arranging 6 distinct letters, we would have 6 factorial ways of doing it. But this time, 3 of the letters are the same. So counting 6 factorial is like saying this way of doing the letters is distinct from this way, which is also distinct from this way. But in fact, these 3 ways are all the same. We can't tell the difference between the A's. So how many times are we overcounting each arrangement when we say 6 factorial? It's not just 3. It's actually 6 times that we're overcounting because there's 6 ways of arranging the 3 A's, A1, A2, A3. I've written them all out here. Therefore, we need to divide 6 factorial not by 3, but by 3 factorial, or 6, which is the number of ways of arranging 3 items. In this video, we distinguished the division rule from the subtraction rule. And we also used the division rule to count numbers of anagrams.